Hi everyone. Today we will be presenting our project design, the Articulate. The Articulate was created by Group 9 and consisted of the following people: Scott Bell, King Chu, Benjamin Sims, and Michael Taub. Motivation. Our motivation for wanting to design the Articulate is because we feel it would be beneficial for workbenches around the world. Imagine this: being able to work on a project without having to deal with shadowing. With the Articulate, the user has the choice to make a hand gesture, and it will control the light to move to the dedicated position, giving the maximum light possible with minimum shadowing. This will allow users to finish and produce projects at a faster rate. Goals and objectives. The Articulate has a lot of great benefits. These benefits include, but are not limited to, a hand-free light for workbenches, able to move through creating hand gestures in view of the camera, being able to rotate the light angle through hand gestures, being able to brighten or dim the light through hand gestures, and it allows for less shadowing when working on a project. General specifications. There were three general specifications that we really wanted to focus on. This was the pitch/yaw and angle/degrees of freedom, robot vision, and environmental robustness. For the pitch and yaw, we wanted plus minus 90-degree movement. Left and right is the yaw, and up and down is the pitch. For robot vision, we used the camera to identify hand gestures to control the movement of the actuations. And for environmental robustness, we wanted to make sure that our design was able to handle any type of temperature that would mainly range from 20 to 100 degrees. And we also wanted to make sure that it was waterproof and dustproof. Key specifications. There were four main key specifications that we as a group decided to focus on. These four were accuracy, durability, actuation time, and computation time. For accuracy, we wanted it to be less than or equal to 1 centimeter of where the user designated the light to go. For durability, we wanted the user to get at least 1,000 or more uses out of it. For actuation time, we wanted it to be between 3 to 5 seconds. This is the time that it takes for the task to be completed for movement. And lastly, computation time. We wanted this to be less than or equal to 2 seconds. We wanted the system to read the gesture within 2 seconds or less. Hardware block diagram. As you guys see, this is our hardware block diagram, which includes all the hardware that we will be using in our design. As you see, it will have a wall plug-in power supply, which will then flow into a voltage regulator, which will then go into a microcontroller, which will control the camera, the motor controller, the servo motors, and the gears, thus making our project work. Next, we will be looking at our hardware components.
We as a group boiled down our microcontroller chip options between the Atmega 328P and the MSP 430 G2553. The Atmega 328P microcontroller was chosen for this project because it is powerful enough to control the necessary devices. It's also a convenient choice because it is natively compatible with the motor controller that one of the team members had before starting this project. It can operate with an input voltage between 1.8 and 5.5 volts and contains enough digital input-output pins to implement the required connections. Although the Atmega 328P currently has a very long lead time, we are lucky to have a team member who had a few of these microcontrollers so we can implement it in our project. The Jetson Nano Developer Kit is an embedded computer made by NVIDIA that is powerful enough to implement deep learning in an embedded environment. It implements the NVIDIA Jetpack, which is a modified version of Ubuntu Linux that is tailored to the hardware on the Jetson Nano. It features a 128-core Maxwell GPU, which allows it to perform computationally heavy AI tasks in parallel using CUDA. CUDA, which stands for Compute Unified Device Architecture, allows a programmer to utilize the GPU for general-purpose computing, which is very useful in machine learning implementations. The Nano also has a high-performance ARM A57 CPU, which allows it to perform general-purpose computing tasks with ease. It features camera serial interface connections, which is more efficient than USB for camera input, as it is both faster and requires less processing from the CPU. It also features a 40-pin GPIO header, which allows it to connect to and communicate with multiple devices. The Nano operates with a 5-volt 2-amp power input and features pin voltages at 3.3 volts.
In the table below, there are 5 different types of servo motors that were thought about to be used in our design. We decided to go with the model MG996R as it had a great voltage operating range from 4.8 volts to 7.2 volts. It also had a decent rotational angle of 180 degrees, meaning that it can rotate between 0 to 180 degrees in both a positive and negative way. Camera. During our research, we found 5 different cameras that we thought would work well with our project. They are the Raspberry Pi Camera Module 2, Raspberry Pi High Quality Camera, the ArduCam IMX219 Visible Light Fixed Focus Camera, the ArduCam IMX219AF Programmable Autofocus Camera, and the ArduCam IMX219 Low Distortion M12 Mount Camera. We decided to go with the ArduCam IMX219 Visible Light Fixed Focus Camera as it was the cheapest and offered a very good frame rate of 120 FPS. Socket specifications using a LED bulb. There were 4 different types of socket sizes that we looked at. These are E12, E19, E26, and E39. For our design, we decided to use a normal household socket, which is the E26. The E26 offers 60 watts of power, 250 volts, luminosity of 800 lumens, is 26 millimeters, and weighs 0.564 ounces. Voltage regulator. There are 2 types of voltage regulators, linear and switching. Linear voltage regulators have low output ripple voltage, fast response times, and low electromagnetic interference, and less noise. However, they're not that efficient. It requires large space, and voltage above the input cannot be increased. For switching regulators, they have a more complex design, which allows for higher power efficiency. Furthermore, it's able to provide output which can be greater or less than the input voltage. However, switching voltage regulators give higher output ripple voltage, it has a slower transient recovery time, is very noisy, and is very expensive.
Pictured here is the software block diagram for the Jetson Nano. The Jetson Nano is responsible for gesture recognition and sending the corresponding signals resulting from these gestures to the microcontroller. The gestures detected are select American Sign Language alphabet letters shown on the left, and the Nano will continually sample the video feed to detect these gestures. This slide contains the software block diagram for the microcontroller. The microcontroller will wait for a serial UART signal from the Jetson Nano. The microcontroller will compare the received command to the programmed available actions and execute it using data sent from the Jetson Nano. The microcontroller will be responsible for actuating the motors and setting the dimness of the bulb. Machine learning software. One of the benefits of using the Jetson Nano is that NVIDIA has many resources for setting up deep learning projects on the device. NVIDIA has released a series of blog posts and video tutorials on these topics, which include pre-trained deep learning models. Using a machine learning library called PyTorch, we can retrain these models with a custom image set and labels, which in our case will be letters from the American Sign Language alphabet. Models from the object detection and PostNet libraries will be used and retrained to cater to the ASL gestures. Machine learning models for gesture recognition. The single-shot detector MobileNet V2 is one of the pre-trained models that NVIDIA supplies with the Jetson Nano. It is a model that uses convolutional neural networks with global average pooling. In the case of accuracy and speed among the object detection models that NVIDIA supplies, it is the best on both accounts. Poe's ResNet 18 hand is a model that uses convolutional neural networks to return segments of the hand. It requires the use of other machine learning models that must be tailored in combination to achieve gesture classification. An example is using support vector machines to apply classification based on the vector outputs of the model. This library is particularly useful because it allows us to easily calculate the direction of the arm movement gesture through the vector outputs. Computer vision software. In many cases on a general purpose computer, Programmatically obtaining image data from the camera connected to the system will require the use of external libraries. However, NVIDIA has implemented this process natively on the Jetson Nano so that no external software will be necessary. Since we are using a camera serial interface connection, the camera feed can be accessed through the CSI0 path on the device. Instantiating the camera feed can be done on one line of Python code, and grabbing image data from the feed can be done on a second line of code. This means that we do not have to install software such as OpenCV, which results in faster and more streamlined programming. So what's the difference between computer vision and machine learning software? The computer vision software is responsible for gathering data from images in a structured manner to be used in a program. They are commonly converted to a data structure called a tensor, which is mathematically like the structures in vector spaces, which is needed to perform the operations in machine learning algorithms in an efficient manner. The machine learning software manipulates these data structures to learn patterns that would otherwise be very difficult at best and impossible at worst to manually extract. Analyzing test cases with a trained model will result in the model outputting a classification or a regression to form a prediction. We will now take a look at the electrical schematics of our system.
This is an overall view of our schematic. Starting from the input voltage from the outlet, the circuit will have two regulators. One to regulate the voltage of 5V DC, which will power the Jetson Nano, and another 5V DC regulator that will power the microcontroller. And we'll have two 5V pins that will be able to power the servo controller if we choose to use one, or use them to power the servo motors directly. We are currently missing the headers and dimmer module for our schematic, but it is a work in progress.
Schematic view of laser calibration. We as a group discussed a way to calibrate our servo actuation and came up with the idea of using a laser sensor array with the laser mounted on top of the arm by the light and the receiver mounted on the base as a detachable module that will be placed roughly in the center of the work area. This would give the system a way to generate an offset for the servo actuation if needed. At this time, we are not sure if this would be a necessary addition to our project, but wanted to have a plan for the event it was needed.
Schematic view of microcontroller. The microcontroller we chose was the Atmega 328P. This microcontroller will allow us to communicate with the servo controller over I2C or send the pulse width modulation signal directly to the motors. Schematic view of motor controller. The servo controller board we selected is a PCA 9685 from Adafruit. This is a 16-channel servo controller, which is far more than we need. However, the board is a low-cost and low-power option that has a module for the Jetson Nano, which makes programming and operating servo motors extremely easy. The controller is powered by 3.3 volts from the VCC pin supplied either by the Jetson or the microcontroller. Communication is handled by connecting the SCL and SDA pins, which enables I2C communication.
In this slide, this shows a schematic view of our power supply and voltage regulator. Functionality hardware starting from the power to the voltage regulator. Basically, we'll be taking the standard power from the wall outlet, which is 120 volts AC, connected to a step-down transformer to reduce the voltage from 120 volts AC to 12 volts AC. From there, we implemented a bridge rectifier to turn the AC voltage into a DC voltage. We added a capacitor to reduce the ripple from the voltage and a Zener diode to obtain a more stable DC output voltage. Once the voltage is reduced from the voltage regulator to a safe operating range for the Jetson Nano would then power everything else from the motor controller to servos and cameras. From the Jetson Nano, it will send a message to the servo controller, which will then send a message to the servo motors, which will activate the gears, and it will allow the arm and light to function based on the user's gesture.
Functionality software. For the Jetson Nano to communicate with the microcontroller, the UART device communication protocol will be used. After receiving commands from the Jetson Nano, the microcontroller will communicate with the other devices through C++ programming.
Articulite frame concept design. For our project, we decided to go with a flexible robotic arm design. The frame will be controlled by two servo motors connected to pulleys, which enables movement in 2 dimensions, pitch and yaw, by using wire guides connected at the top of the frame where the light socket will be located. The frame was designed in SolidWorks and 3D printed, which enabled us to rapidly prototype each component. Rapid prototyping initial design of frame. Our initial design was to have a rigid frame of interlocking segments. Once assembled, the frame was very rigid, holding any position it was moved into easily. It also had a high degree of mobility in all directions and was very light in weight. Rapid prototyping wire guide. Once we were satisfied with the structure, the wire guide was modeled as a square with guide holes located in the corners, each wide enough to add a gasket which would prevent the wire from damaging the plastic during movement. Then the edges were rounded for aesthetics and safety while articulating. And finally, the wire guide was then combined with the interlocking segment, and once printed, the structure was assembled. Rapid prototyping fully assembled frame. We connected the frame to a pulley to see how the movement would work once fully assembled, and found that this design was too rigid, where the system would crimp when movement in multiple directions occurred. The frame would also rotate, causing the wires to get wrapped around and tangled around the frame. Rapid prototyping new and improved design. The segments were redesigned, adjusting the dimensions of the interconnecting spheres, which made them much looser. Channels were also added to the female connection side, along with corresponding bearings on the male side. This prevents the system, when connected, from rotating. Alternate design of frame. Currently, we have decided to go with a continuum robotic arm design. This was done for 3 reasons. First, it's a simpler frame to design for. Second, the system gives much more flexibility. And third, the design will allow us to easily implement compression springs to allow extension and contraction, which is one of our stretch goals. The previous design is still an option. We have not yet settled on which version to implement.
Lastly, we will look at power options. Wall plug-in. Our wall plug-in power supply is going to be plugged into a wall outlet, which will be providing 120 volts AC. The cord length of our wall plug-in is 12 feet. However, the actual length from our project to the wall outlet is going to be about 8 feet. Some specifications of using a wall outlet is stable voltage, able to plug into an extension cord for extra length if needed, and there's no discharging of voltage. Battery pack power supply. We thought about incorporating a battery pack power supply in our design. That way, we can make our project portable. Furthermore, battery pack power supplies offer stable and clean power, as well as different possible types of batteries that can be used as shown in the table below. For our design, we tested a battery pack power supply using AA batteries. Next, we will be looking at the administrative part. Work distribution. As you can see in the table below, King and Michael focused on more of the hardware, such as the input power and voltage regulation, and Ben and Scott focused more on the software aspect of the programming and the gestures for the camera. Budget and financing. In the table below, it shows all the parts that we ordered and the cost of each part and the consumer from which we bought the parts from. As you can see, depending on the quantity of the parts, our cost ranges between $326.64 to a max of $425.47. Project progress. As you can see in the bar graph, it is separated in different sections of how we based our overall completion of our project. In blue is research, red is design, orange is parts acquired, green is prototyping, black is building, and purple is testing. The numbers are also color coded, and our overall completion of our project is 69.17%. Constraints that we found when prototyping. So far, we found two main constraints. First one is the core length for power source, and secondly, when we tried to incorporate the battery pack power supply to create a hybrid power mode, we found that when our design was powered by AA batteries, it lasted about 10 minutes before the batteries were fully drained of its power. We have finally reached the end of our presentation. We will now answer any questions that anyone may have.